Hello, my name is Konstantinos Tassis and I'll talk to you about PASIPHAE. PASIPHAE is an experiment that seeks to revolutionize the way the foreground due to galactic interstellar dust is removed by experiments seeking an inflationary signature in the polarization of the cosmic microwave background. PASIPHAE, as you can see, is an acronym, but very much like Gaia, it's also a name, that of the Minoan Queen. And let me start by introducing the team. PASIPHAE is an international collaboration spanning 4 continents between Forth and the University of Crete in Greece, IUCA in India, the South African Astronomical Observatories, Caltech in the United States, and the University of Oslo in Norway. And these are our sponsors so far. PASIPHAE aims to address the thermal dust polarization foreground of the CMB. The early universe is not the only source of polarized microwave emission. Cold, elongated galactic dust grains aligned by the galactic magnetic field, and so also emit polarized microwaves that you can see in these bluish hues on the sky map. Their polarization direction depends on the direction of the magnetic field. The way the dust foreground is subtracted from microwave maps so far is the following. Here I'm showing the various contributions to the microwave sky. It's a busy plot, so let's focus on the 2 ingredients relevant to the problem, the CMB and the dust. Galactic dust, although very cold, around 19 degrees Kelvin, is still warmer than the CMB, which is of course at the 3 Kelvin, and so it dominates the emission at higher frequencies. So you map the dust at higher frequencies where it dominates, and you scale and subtract the signal from what you see at around 100 gigahertz, where the cosmic signal, the cosmic microwave background signal contributes significantly. This technique works well for scalar quantities such as intensity, and so the CMB science so far has been tremendously successful despite the presence of galactic dust. But this is not the case for polarization. There is a problem more severe than originally thought, and it has to do with the 3-dimensional structure of the interstellar medium. As our group first pointed out in 2015, you can get a situation like the following. 2 clouds lie along the line of sight. One dominates the emission at high frequencies and the other at low frequencies. The polarization pattern then rotates between these frequencies, trying to trace the magnetic field of the dominant cloud in each case. This line of sight frequency decorrelation, as we call it, of the polarization pattern has been studied by several groups since, but there has no been a consensus among these studies because the effect remained elusive and unconstrained until very recently. But there is now evidence that this effect is actually present in Planck data. The key in the identification of this effect, of course, is to know where to look for it. And that's where 21 centimeter H1 data comes to the rescue in 2 different ways. First, H1 spectra can be used to identify locations of the sky where the line of sight intersects multiple clouds. And second, high-resolution H1 channels reveal thin linear structures that are statistically aligned with the magnetic field as traced by starlight polarization. Clark and Hensley in 2019 inferred the direction of the magnetic field indirectly from the morphology of these H1 clouds structures, and they defined a 3D map of the Stokes parameters of linear polarization. Using this H1 data, we identified sightlines that were susceptible to the line of sight frequency correlation effect by intersecting more than one cloud with misaligned magnetic fields. These locations make up our target sample, while the sight lines that intersect only one cloud, and thus no line of sight frequency decorrelation is expected, make up the control. We selected pixels from the Planck 353 and 217 GHz polarization maps for each of these samples and computed the sign difference between their EVPAs. Because the target sample pixels are selected to have higher likelihood of large line of sight frequency correlation, we predict larger angle differences between the two frequencies for the target than for the control. And indeed, this is what we see. Here I show the distribution of EVPA change between the two frequencies, 353 GHz and 217 GHz. And I show it for three different sets of pixels. All the Planck pixels of the high galactic latitude sky in black, the control pixels in blue, and the target pixels in orange. D is the spread of these distributions. The difference in D, the spread, between target and control samples that you can see by eye is statistically significant and is robust against how you subtract the CMB, what algorithm you use to make the maps, the noise level of the two sets of pixels, and even residual systematics. In fact, correcting for Planck residual systematics increases the significance of the effect. And let me remind you that the selection of the target and control samples is astrophysical and knows nothing about Planck and its systematics. And not only is D different between target and control samples, but it increases monotonically as the misalignment between clouds, shown on the x-axis, increases, exactly as we predicted. So now that we have demonstrated that the effect is visible in the Planck data, the need to find ways to account for it when cleaning microwave maps before using them to study the early universe got more urgent. And PASIPHAE seeks to remedy this. The same dust grains that emit polarized microwaves also absorb starlight and impart polarization on the emerging light. So we can use stars of known distances as lampposts. If we measure the polarization of many stars of different but known distances along the line of sight, then we can infer the direction of the magnetic field between them and use this information to subtract the dust foreground from the CMB polarization, including the three-dimensional effects. And this approach is only now possible because of Gaia and PASIPHAE. ESA's Gaia mission has delivered reliable parallaxes for 1 billion stars, and PASIPHAE will deliver the necessary polarization measurements. And for the first time, we will be able to construct a tomographic map of the galactic magnetic field direction. PASIPHAE survey will cover the high galactic latitudes that CMB polarization experiments target. It will run concurrently from two sites in the northern hemisphere at the Skinnacas Observatory in Crete, in Greece, and in the southern hemisphere at the South African Astronomical Observatories in Sutherland. These are the vitals of the survey. We'll observe all stars brighter than 16th magnitude in the R band, and we hope to cover 1,500 square degrees per year. PASIPHAE will measure the polarization of several million stars in a part of the sky that is essentially unexplored in optical polarization. I'm showing here the number of stars per square degree with currently measured polarization properties as a function of galactic latitude. The high galactic latitudes of interest have been neglected, and the current state of the art is disheartening at less than 1 star per 3 square degrees. The reason, of course, is because these studies are driven by the star formation community that cares about the galactic plane where stars are forming inside molecular clouds. But PASIPHAE will take us to at least 360 stars per square degree. This is a 1,000-fold improvement over the current state of the art. To achieve this, both systematic and statistical uncertainties will have to be below 0.1%. We need this kind of unprecedented accuracy because of at these high galactic latitudes, there is little dust, and so the polarization is low. This is achieved by WALOPs, two innovative, wide area, linear optopolarimeters designed specifically for this project. WALOP builds on the well-tested, no moving parts, low systematics technology of RoboPol that has been running on Skinnacas with tremendous success since 2013, and it basically implements the RoboPol design in a wide field instrument. Its development is currently underway at Ayuka, India, and the commissioning is expected this year. For more details on the instrument design and the calibration, please see the posters by Ramiya and Siddharth. Since we are pushing the envelope, though, of polarimetry with this program, systematic uncertainties is the major obstacle for reaching such low optical polarization levels. The last 4 years, we have been observing a large number of stars with RoboPol to establish stable polarimetric standards down to 0.1% all over the target area of the sky. The resulting list of polarimetric standard stars will be published this summer. And while WALOPs are being developed, we have used RoboPol for a pathfinding first demonstration of the magnetic tomography technique. We picked a region of the sky where we have two clouds overlapping, but only partially. And of course, we used H1 position velocity data cubes to do this. So we have one region, the red circle, where the only cloud along the line of sight is this nice elongated cloud that you can see on the left. I will call it the baguette cloud. And the neighboring region, the black circle, where we have an overlap of this baguette cloud and this croissant-shaped intermediate velocity cloud that you can see on the right, which presumably lies further away. We measured the polarization of many stars in both regions, as shown in the upper panel, and combined them with Gaia distances. And the result is shown in the lower panels, where the line segments mark the mean magnetic field direction of the clouds, the foreground on the left and the background on the right. The mean magnetic field direction of the foreground elongated cloud is consistent in both circles and seems to follow the morphology of the cloud. The mean magnetic field direction of the background croissant-shaped cloud, which is only recovered in the black circle, where there is an overlap, is significantly misaligned with that of the foreground cloud and forms an angle of around 60 degrees. Okay, say we got the 3D map of the galactic magnetic field direction. How can we use this information to aid the CMB foreground subtraction? The obvious question here is that PASIPHAE maps polarization in absorption, stellar polarization, but the CMB foreground is in emission. So how do we connect absorption and emission? We take advantage of the fact that optical stellar Q and U, absorption-induced Q and U Stokes parameters are extremely well correlated and predictive of emission Q and U, as Planck has established. What happens right now in the map and subtract scheme is that a modified blackbody model for dust emission is fitted per pixel based on high frequency data and extrapolated to lower frequency data. We can instead fit a fancier model where a modified blackbody model is fitted per cloud using H1 maps to find the edges of the clouds and scale their emissivities, and the magnetic field direction in each cloud, as measured by PASIPHAE, to set the relative values of Q and U that give you the polarization angle in each cloud. If you have more than one clouds along the line of sight, then you naturally add up the Stokes parameters from each. Then one can use this model that includes the three-dimensional effects to subtract the foreground. Our colleagues at the University of Oslo are developing this method right now. Going beyond the orientation, though, we claim that we can actually estimate the strength of the field in each cloud individually as well. But the methods available so far for these estimates are not accurate enough. The strength of the magnetic field is usually estimated from the spread of the polarization angles and the RMS velocity of the gas of the cloud by a method developed in the 50s by Davis and Chandrasekhar and Fermi. This method relies on the assumption that the observed spread in the distribution of polarization angles is due to the propagation of the so-called Alfvén waves, which are incompressible waves. And it's not very accurate when tested against simulations of supersonic MHD flows, which are conditions relevant to the interstellar clouds. The black solid line, marked F equals 1 here, shows the relative deviation of the Davis-Chandrasekhar-Fermi estimated magnetic field strength from the true value in 5 different MHD simulation models of different Mach numbers marked on the x-axis. To correct for the overestimation of the magnetic field, which, as you can see, can be very large, usually a fudge factor is introduced, and it's shown here by the black dashed line. Or sometimes a more sophisticated method of measuring the spread of polarization angles is used, like the one developed by Hildebrand and Wood in 2009, shown here in blue. Observations, however, indicate that the non-Alfvénic compressible modes may be actually important in the ISM dynamics and energetics. In a recent paper with my PhD student Kalidis, we propose a new method for estimating the magnetic field strength, which includes the compressible modes. Our method, which, as you can see, comes down to a minor alteration of the Davis-Chandrasekhar-Fermi formula, outperforms the previous methods, which are based solely on incompressible Alfvénic modes, and achieves a mean relative deviation of around 17% without the need for a correction. So although PASIPHAE science is driven by the hunt for B modes in the polarization of the CMB, its impact will be very wide. First of all, the 3D tomographic map of the galactic magnetic field direction by itself will revolutionize our ability to approach questions such as what is the origin of the galactic magnetic field? Is the magnetic field dynamically important in interstellar clouds? And even what is the origin of ultra-high energy cosmic rays? And second, polarization measurements from our survey will reveal in stellar astrophysics intrinsically polarized stars and in high energy astrophysics synchrotron emitters. And of course, there is always a great potential for serendipitous discoveries with these novel science products. Thank you very much. For more details, please check out our webpage or the PASIPHAE white paper, which is on the archive. Thank you for your attention.